Hey there, thank you for clicking on this video. In this lesson, we are going to explore what is E and the natural log. Now, if you're looking at the timestamp to this video, it's probably a little bit longer than most of the lessons that I post, and that is because the practice set is included in this. Once we establish what E and the natural log are, there's actually not enough new content to justify an entirely separate video with review because nothing else changes. So please don't be put off by a big, time, like a long video here, because I promise it includes more. So please give this video a quick thumbs up if you find it helpful. Subscribe to the channel for more math content. Drop a comment or ask a question below, and check out many of the other videos and playlists on the channel. I will be sure to link some at the end of this video for you. So we're going to start off with trying to establish what is this number E. And I will often ask my students at the start of a lesson on this, what letters do we commonly see as variables? What are the letters of the alphabet we use? And they will, of course, answer, oh, we see X a lot and we see Y. Those are probably the most common ones that we use in algebra. If we need a third variable, sometimes we'll be using a Z. We'll see N's a lot, like N just for a number. So we'll see N. If you're doing an application problem, maybe time is what you're being asked for. So we'll see T's, but we rarely, if ever, see a lowercase e. And there is a great reason for that. It is because E is used to represent a number. But what is it? So short story, like pi, E is a number that occurs in nature. So if you are exploring pi, your teacher might give you a bunch of circles. I remember doing this in 6th grade because I remember the classroom where we were asked to bring in circles. So lids from coffee cans and things like that. And then we took yarn and we used yarn to measure the circumference, and then we measured the diameter. And so we would divide out the circumference by the diameter, and what all the kids would realize, like no matter whether you had a big circle or a small circle, you were getting the same number or something close to the same number. And so you would see that this number occurred in nature, and then the teacher tells you, oh, this number is pi. Great. E is sort of like that. It's this number that appears in nature in a lot of unexpected places. We'll talk more about that towards the end of the lesson. Now, this lesson is going to cover some key ways that we can conceptualize this and see where it comes from. That's going to be the bulk of the front part of this lesson. And then we'll look at how it's applied, how it relates to things that we've already covered in this lesson sequence on exponentials and logarithms. Now, this is an in-class activity that I do with my classes, and I kind of want to walk you through it. It's just a way for students to see how this number can turn up in nature. Now, you'll see from my data, this is one of those activities that isn't necessarily great if just you do it, because it relies on statistics here and it relies on having a lot of data points. So you'll see what I mean. Here's what the activity looks like. You consider a grid with the numbers 1 through 64. So something that looks like this, and you've got the numbers 1, 2, 3, 4, and it goes all the way up to 64. And then you'll use a random number generator to generate 64 random numbers. Most graphing calculators have a random number generator on them. You can also find websites. I usually direct my students to a website, and they'll set the random number generator to generate only numbers 1 to 64. And then as you're generating the 64 numbers, you mark them off on the grid. Duplicate numbers count. So what we mean by that is if you get a 2 twice, you don't like discard the second roll and say, oh, we need a different one. That counts as one of your 64 random numbers, okay? Because if you waited until you got new numbers all the time and you just threw out the duplicate numbers, well, the grid has 64 numbers on it and you're generating 64 random numbers. So if you keep skipping them, then what would happen by the time you got all of them is you would mark off all 64 numbers, and then everybody has the same grid, and that doesn't tell us anything. Interestingly, I teach an electronics class, and that class we design random number generators and learn about some of the electronics behind how like your calculator would get you a random number. And so my students do random numbers just 1 through 6, but you could expand it to do any number. Now, when you have generated 64 numbers, you're going to find the ratio, not ration. The ratio is 64 to the number of unmarked squares. So you're going to take the number 64 and divide that by the number of unmarked squares. And that's why you don't keep ignoring duplicate numbers. So you're going to find 64 random numbers, but in the end, you're going to have some duplicates. And that means some of the numbers aren't ever going to be called. Okay, that's totally fine. That's what we want. All right, so here's what we have in mind. So there's a grid of numbers 1 through 64. And I actually, as part of prepping to record this, went to a random number generator and did this all myself. So I tallied up 64 like rows or generations of random numbers and then marked them on a piece of notebook paper and listed them out. And here's what we got, okay? So those were all the unique numbers that I was able to get. Some of those numbers came up more than once. So you'll notice, say, like the number 2, I never got at all. And that's because maybe number 1 came up twice, okay? And then I went through and I marked all of them off on this grid. Okay, like so. And there you can see the visual picture of it. And obviously I have some numbers that are not marked. So we have like some numbers here. And so you can see them. And it turns out I have 26 unmarked numbers out of the 64. So now I'm going to find the ratio of 64 to 26. And that gives me that number right there. So 2.4615, so forth. Okay. Now, this number is a little bit low, okay, because we will look at the number that we're expecting to get. But again, I only did one trial. As many groups of students complete this activity, we see them begin to cluster around the true value, which is pretty cool. So this individual trial ended up a little bit lower than the number, but I will have students do this same exercise in class, and they will end up with like 3.1. or something is their number. And then what we do is we look at a bunch of different groups and we average all of the totals together. And we start to see that statistically, we end up clustering around the true value of E. And ideally, I will actually hold the trials from, say, my first class and then add the second class to that and add the third class to that, however many algebra classes that I have, so that we can create a bigger pool of numbers, because the more data points we have, the better this activity actually works. Now, we can also get this using the formula. So this is the formula 1 + 1 over n to the nth power. This is used in compound interest. So if you've done a financial class, you will have seen a formula that looks like this. Instead of like ones, you might have like an interest rate in there. And yeah, so that kind of pushes into our statistics kind of realm. But what we're going to look at are different values of n. Now, what I did here was I started with n equals 1 and then went to n equals 2 and then started to make them bigger in bigger chunks, because if we do like 1, 2, 3, 4, we're going to see something happening, but what we really want to see is what happens as n gets really big. Now, in higher level math, usually beyond the algebra level, what we're actually doing here is looking for something called a limit. All right, and I'll go over that in a little bit. So when we say n is equal to 1, n is equal to 2, n is equal to 10, and so forth, this is what we mean. So you're going to take 1, n is equal to 1, and plug in a 1 everywhere you have an n. Here plug in a 2, so it'd be 1 + 1 over 2 all squared, 1 + 1 over 10 raised to the 10th, and so forth. And what we want to notice is as n is increasing, what is happening to the value of that expression? Is it getting infinitely big, if I were to go out to like n equals 10,000 next, what would that mean? Well, let's take a peek. So it starts off as just 2. Okay, so that's where it starts off. And then when I increase by 1, we go up by 1/4. Now, notice what's happening here. The first one sent it up by 1/4, but now I'm going up by 8, and it went up like a little bit more than 1/4, but it's definitely not a linear relationship. It's not going up by 1/4 every single time. So that 3 is 2.5, and 4 is 2.75, and 5 is 3. Like, that's not happening. Here, I went up by 90. Okay, so like I went up by 1, I went up by 8. Now I went up by 90. And you'll notice that the value of that expression now just went up by like a little over a 1/10. So it was about 2.6, like a little bit under 2.6, and went up to a little bit over 2.7. So not a big increase for going up by 90. Now I'm going to go up by 900. So like basically we're making it much, much bigger. And you'll notice I didn't even go up, like what did I go up there? Like a little over 100th. So what we want to notice about this is that as I am making n bigger and bigger and bigger, and you can try this on your own, go pause the video, grab a calculator, try n is 10,000, and see what happens. But what the key here is that my value for that expression is not exploding. It seems to be leveling off somewhere. Okay, note that the value is not getting infinitely big, even though I am really pushing the, what n is. It is leveling off. It does not appear like this is going to go past like 2.7. Does not appear like that's going to happen. The number is it is leveling off at is the value of E. And so you get an idea here, even though it's early in your math career if you're an algebra student. Now, if you're watching this as a pre-calculus student, then you are very likely going to see this in a pre-calculus class. But it's leveling off, it's approaching a limit, and that limit is E. So that leads us to answering the question, what is E equal to? And I am going to say there's I put a 1 in the approximation a little bit too early when I wrote it down. So just heads up on that. You'll see what I mean. I'll fix it when I get to it here. So first off, it's called Euler's number. So if you're wondering, what is the name of it? What do I call this number? Honestly, most of the time we just call it E, but it is called Euler's number, not Euler. Okay, that is Euler. I'm not saying it wrong. It is irrational like pi, so it never terminates and never repeats. And it's approximated, and this is where I have the error. Here's what it is. 2.7182881. Like I put the 1 in just like 18281. Like I just put the 1 in a little bit earlier. Most of the time we're just going to do this. So I just wanted to, that's just called, I'm a human being typing up my slide. So that's what it is. We almost never are going to write it out. If you kind of remember that it's about equal to like 2.71 or 2.72, that's fine. Just like with pi, most of us think of pi as 3.14. We know that there's more digits to pi than that, but for what we need it for, it's fine. All right, so where does E turn up? I mentioned at the beginning of the lesson that this is a number that turns up in nature. So as you are studying science and you're exploring different relationships in the world around us, like where are you going to see E? All right, so some interesting places. Population increases. So that would be the population of, say, bacteria in a petri dish, the population of, I don't know, some city. Radioactive decay. So you got some radiation, want to find out when it's going to be safe. Continuously compounded interest, that's where I usually go in the application direction with my students. Heat transfer, so going something, you have something hot, you put it into something cold. Basically, anywhere there's continuous exponential growth or decay, you're going to see E pop up. Logarithmic spirals, and you will see these in biology, in cell shapes, seeds, in plants. You can see it in like spirals. Including spiral galaxies, like you're doing those kind of calculations, the number E is going to show up. And in statistics, when dealing with the bell curve, that's like your normal curve. So this number does turn up. Okay, it's not just a random thing that you encounter in your algebra class and, call it a day. All right, so what does this mean for our study of logarithms? And this is where it's kind of this add-on. When I teach this to my students, we don't spend a lot of time on it because you really already know everything you need to know. We just need to go over some vocabulary and some notation. So log base E is known as the natural log. So in our study of logarithms, we've talked about logs of a base B, and we've talked about like log base 2 or log base 3. We know that log base 10 is the common log, meaning if you don't see a base written, it is assumed to be base 10. So log base E is actually common enough that it gets its own name. So where this is the common log, this is called the natural log, and it is important enough that it gets its own symbol. So we do not actually write out log base E. I don't prohibit my students from doing it because I want them to remember what it is and to connect their natural logs with everything else that we know about logs. But I will discourage them from writing it and encourage them to move on from that as soon as they're comfortable. So here is the symbol for it. So log base E is ln. So if you see an ln, that is for log natural. Okay, L for log, N for natural, and that is our symbol for it. This is an L. This is not a capital I or the number 1, and you can see why there is confusion here, because the capital I does look pretty similar to a lowercase l, okay? And I will put this in capital letters on slides in my room. I will jump up and down, wave my arms. This past year, I had students go onto ChatGPT or Gemini and have it generate like a 30-second little song about L's and how that's an L and it's not an I and it's not the number 1. Not any of those things. And I still had students on their unit test write IN. It's not an I, it is a L. It's an L. So L for log. Okay, that's a natural log. Now, this is a separate key on your calculator. Everything else that's true about logs is true here. So you will usually see it if you can find the LOG key on your calculator, you will see the LN key right with it. And often the secondary function on that, you will see E or possibly E to the X. So if you needed to do E to a power, you would hit your second or shift key, depending on the model of calculator that you have, and you would then hit the LN button. That will give you E. Okay, E to whatever base you wanted. That's and often they're on the top of the calculator or sometimes down the left-hand side. Just you want to make sure you know where to find it. If you're using Desmos, you can just type in the letters LN, and that would be fine. You can go into a menu and find it too, but you can just type in the letters LN. So this gets to the examples, because there really isn't anything new in terms of how any of this stuff is executed. It's just you might see an E or you might see an ln. So if you were asked to solve an exponential equation, you would do this the same way you would do any of them. You would want to isolate your exponential first. So in this problem, there's our exponential. So I am going to start this problem by dividing both sides by 2. So I get e to the 3x minus 1 equals 4. And then just like you would undo the exponential by taking the log of both sides, matching the base up, this is what you would do here. So normally we would say like, okay, if I want to undo the base of e, I would take log base e, but I would encourage students to not write this. Okay, I would encourage them to go to ln. Okay, and so they would just do it that way. And then if you watched the video, we know that the log of the base undoes the base of the exponential, leaving us with just the exponent. So 3x minus 1 equals the natural log of 4. And now you've got your options. You can go to a calculator, evaluate the natural log of 4, or you can execute the rest of the problem without evaluating the log so that you're getting the accurate answer. Now, we do want to be a little bit careful here. If I add 1 to both sides, okay, technically this is fine. Order of operations implies that you will take the natural log of 4 and then you will add 1 to it, which is the correct order. If you go back up a line, okay, I could, in this line, take the natural log of 4, and then I'd have a number here, and then I would add 1 to that number. That would be true here. You would take the natural log of 4 and then add 1 to it. You would not do 4 plus 1 is 5 and then take the natural log of 5. You are not taking the natural log of that 1 at all, and you don't want to embed it in. Now, to avoid that confusion, what people will sometimes do is instead of doing natural log of 4 plus 1, they would do 1 plus the natural log of 4. So they would just use the commutative property of addition to switch the order of it. And that way there's no confusion about what goes where. You're not going to accidentally throw that 1 into the natural log. So that will not happen. That is like kind of up to you, just like be careful. And then we would divide both sides by 3. So technically the exact answer to this is 1 plus the natural log of 4 all divided by 3, or you might need to do a decimal approximation of that. And I'll try to get a decimal approximation of that momentarily. So 1 plus natural log of 4 all divided by 3, and that's about 0.795. So 0.795. And of course, this is the exact. That makes mathematicians happy. This is an approximate. That makes scientists and engineers happy. So there you go. But nothing about that was different. We're just dealing with a natural log. Properties of logs, I decided to do an example of a collapse problem instead of an expand, but on the practice problems, like I'll give you one of each. So this is, as with the other ones, doable in one step. You would have here the natural log of x to the 4th, y to the 6th over z cubed. You can jump right to the answer, or you can do this in steps. So you would start with moving those into the exponent. So natural log of x to the 4th plus natural log of y to the 6th minus natural log of z to the 3rd. When you add logarithms, so this is this property of logs, if you are adding logarithms, that's the same as taking the log of the product. So this would be the natural log of x to the 4th, y to the 6th minus natural log of z to the 3rd. And if you are subtracting logs, that is the log of the quotient. And so we would do the first argument, x to the fourth, y to the sixth, divided by the second argument, which is z to the third. Ta-da! Wonderful. Pause the video or rewind it if you just kind of need to go through that again. That is the beauty of a video and the internet, is you can make this work for you. And I will move on to the next slide. So here are the practice problems. 2 equations to solve and 2 properties of logs, just one to expand and one to collapse. Like I said at the beginning, this is really not a long enough piece of content to warrant a whole separate video for it. So pause the video here, work these problems out on your own, and then come back and we'll go over them together. Okay, so for this first one, let's take a look at this. So we would start by trying to isolate our exponential, which is the e to the x plus 4. I have a 1/2 multiplying out front, and I have a -3. So I'm going to start by undoing the subtraction by 3 to get 1/2 e to the x plus 4 equals 8. And then to undo multiplying or dividing by 2, I'm going to multiply by 2. 1/2 times 2 is 1. Okay, like if you're right here. Or 2/2, if you have 2/2 of something, you have 1 of them. So that gives us e to the x plus 4 equals 16. And then you can write log base e if you want to remember how to do that. Or what would be preferred is just take the natural log of both sides. The natural log of e to the x plus 4 is just going to give you x plus 4. And that's the natural log of 16, and then we're going to subtract 4. Now, you can do natural log of 16 minus 4, but as before, that can sometimes cause some issues because somebody somewhere is going to do 16 minus 4 is 12, and then take the natural log of 12. So what is very common is instead of natural log of 16 minus 4, you would see -4 plus the natural log of 16. That is our exact answer. And then if you are in scientist or engineering mode, you would do -4 plus the natural log of 16, and we get -1.227. So x is approximately equal to -1.227, and that is approximate. Okay. Moving on. Second one, there's my exponential. I need to be able to isolate that first. So we'll start here by subtracting 2 from both sides. So 4e to the 3x is equal to 8. And then divide both sides by 4 to get e to the 3x equals 2. Take the natural log of both sides. So natural log of e to the 3x is going to give me just 3x is equal to the natural log of 2, and then dividing both sides by 3, x is equal to the natural log of 2 divided by 3. That is our exact answer. And if you are in the market for an approximate answer, we would have the natural log of 2 divided by 3 gives us 0.231. So x is approximately equal to 0.231, and that is my approximate. And there we have it. So 2 equations. Everything that was covered in earlier videos regarding how to solve exponential equations using logarithms is the same here. If you are kind of losing it here, what I'll do is I will link to the video that goes through that. You can kind of back it up and see that video. You might also want to go back and look at what is a logarithm. I cannot link both of those videos, so I will link one of them up there, and I will link both of them in the description box. So be sure to go back and check those out if you need to. All right, next two are our expand and collapse. So this is using the properties of logs, exactly the same as what is covered in the properties of logs lesson, except that we have an ln instead of like another log. These are doable in one step. So we've got here, this would be 3 natural log x minus 4 natural log y minus 2 natural log z. Totally doable in one step. Now for this one though, what I am going to do is actually rewrite this. I'm going to do it using a property of exponents and a property of logs instead of using two properties of logs, because we often end up with like a sign error in the subtraction. So what I'm going to do on this one is start by doing a property of logs or exponents, where we remember that if something is in a denominator and I don't really want it as a fraction, I can write it as a negative exponent. So 1 over y to the fourth is y to the negative fourth, and the same with 1 over z squared is z to the negative 2. And back when I taught this, and I say this to my students all the time, this is about flexibility. When you learn something like what is a negative exponent or what is a rational exponent, we're going to see that in the next problem. What you're learning is some flexibility, so that if you would rather have a positive exponent, you can write something as a fraction. If you would rather not have the fraction, you've got a way to rewrite your expression without it. Now, what this does is it turns all of these into multiplication. And that allows us to apply this property that if you see something multiplied in the argument, that would be adding the individual logarithms together. So I can do natural log of x to the third plus natural log of y to the negative 4 plus natural log of z to the negative 2. I don't know why I converted to a cursive L and then out of a cursive L. There's no rhyme or reason to that. And now we'll bring the exponents down front. And so that becomes 3 natural log x plus negative 4 natural log y plus negative 2 natural log z. But of course, adding a negative is just what subtraction is. And so you don't have to write plus a negative there. That is just minus. And that way of doing it might make it a little bit easier to not forget that it will be a minus 2 natural log z. I know in earlier videos I said, like, listen, if it's in a denominator, it's gonna end up negative. Make sure that you're subtracting everything that's in the denominator. That can be easy to forget, or it can feel a little hocus pocusy, and we don't want stuff to feel hocus pocus in math. We do want it to make sense. Okay, so for this next one, we have the coefficients. And you can do stuff similar. So you can use the division, or you can do what I just did and kind of move the negative with the number. So we'd have natural log of x to the 1/2, and you could do minus natural log y squared like I did earlier, or you can bring the negative with it. And so you bring like a negative 2 up into the exponent, and then that becomes a plus sign. And then here, this is a negative 1. Okay, or you could leave it as a minus z, natural log z. Like, you've got options there. Now what this does is this makes this all the same operation. So instead of having some addition and some subtraction, we actually are dealing with all addition, which means that we can just use that one property, which is kind of nice. So this is natural log of x to the 1/2 y to the negative 2, z to the negative 1. And we're basically going in reverse order here, where now I have negative exponents. I'm going to kick these down into the denominator. Okay, so we'll have x to the 1/2, and then this would be y squared z to the first. And then the last thing you might do is remember this fun little fact that an exponent of 1/2 is a square root. So this would be square root of x, y squared z, and we don't have to write an exponent of 1. Okay, is that doable in one step? Yes. Is that a little bit trickier to do in one step? Also true, but not impossible. So there you go. You got a couple of practice problems to go with this, exactly the same as other videos, except with a natural log and using an e instead of using other numbers. Okay, so there you have it. And that was the lesson and the practice set in about 35 minutes. So again, I didn't feel like that was worth 2 totally separate videos. Please don't forget to give this video a like if you found it helpful. It only takes a second to do that, and it really helps out the channel. Subscribe to the channel for more math help. Drop a comment or ask me a question. Just if you're going to criticize the fact that I had a typo, just be gentle, okay? Like when I get a chance, I can, like, I guess, record another lesson. But check out the many other videos and playlists on the channel, and I will link some of those below for you to check out. And I hope I see you in a future video.